Let's have the salt of a weak acid and a weak base as the final example. Consider the formation of ammonium acetate solution. Ammonium acetate also is a very soluble salt capable of forming much concentrated solution. It's a salt, hence a strong electrolyte. In water, it dissociates to give ammonium and acetate ion. In this case, cation as well as anion have a high charge density and react with water to cause hydrolysis. It shows cationic and anionic hydrolysis both. The hydrolysis of cation and anion are independent of each other. They are generally different. The species which is the conjugate of acid or base having a higher value of dissociation constant shows less tendency to hydrolyze. Depending on the relative tendency to hydrolyze, that is the dissociation constant of the corresponding acid or base, cationic or anionic hydrolysis may dominate. If cationic hydrolysis dominates, the solution will be slightly acidic, and if the anionic hydrolysis dominates, the solution will be slightly basic. These two reactions are independent of each other. The only common fact is the concentration of the salt. In the case of monobasic weak acid reacting with a monoacidic weak base to form salt, the cation as well as anion will have the same concentration. As such, we must have 2 degrees of hydrolysis, which may be denoted by H and H dash, or maybe H1 and H2. In a rare situation, when Ka is equal to Kb, cationic hydrolysis will balance anionic hydrolysis and the solution will be neutral. A very specific example of this type is ammonium acetate. This is one of the rare salt which has equally weak acid and base part. This is one salt where the degree of hydrolysis is the same for the cation as well as the anion. So in this rare salt, we can use the same value for degree of hydrolysis of both ions, that is H. In this case, ammonium ion and acetate ion interact with water to form acetic acid and ammonium hydroxide. Taking the degree of hydrolysis to be H, the concentration of ammonium ions in the solution will become C1 minus H. Acetate ion again is C1 minus H, while the concentration of acetic acid would be CH and ammonium hydroxide would be CH. The hydrolysis constant KH is simply the square of degree of hydrolysis. Now this allows us to take the degree of hydrolysis as simply the square root of hydrolysis constant. The solution is neutral as the hydrolysis of cation as well as anion is the same. The hydrolysis equation can be obtained by addition of 3 equations that we have done earlier, namely the dissociation of water, the dissociation of ammonium hydroxide, and dissociation of acetic acid. Writing the 3 equations, the first one is autoionization of water having the equilibrium constant as ionic product of water, Kw. The second equation is the dissociation of acetic acid having the equilibrium constant as Ka. And the third is the dissociation of ammonium hydroxide having the equilibrium constant as Kb. If the second and the third equation are subtracted from the first, the equation obtained is the same that we have written for the hydrolysis of ammonium and acetate ions. If the 2 equations are added, the equilibrium constant of the resultant equation is the product of the equilibrium constant of the 2 equations. If one is subtracted from the other, the equilibrium constant is of the resultant equation is the equilibrium constant of the other divided by 1. The hydrolysis equation is obtained by subtracting the dissociation of acetic acid and ammonium hydroxide from dissociation of water. Hence, using this concept, the hydrolysis constant is ionic product of water divided by the dissociation constant of acetic acid and dissociation constant of ammonium hydroxide. Using this expression, the degree of hydrolysis is the square root of ionic product of water divided by the product of dissociation constant of acetic acid and dissociation constant of ammonium hydroxide. This particular salt is neutral, but this is not a general case. Mostly, the acid or base is stronger than the other, and the solution might be acidic or basic. The notable fact in this case is the pH of the solution is independent of the concentration of the salt. Of course, we have to take the concentration high enough so the contribution from water can be neglected. We will not go into the derivation of the equation of the pH of this type of salt. Simply, the equation to be used is pH is equal to 1 by 2 pKw plus pKa minus pKb. This way, we can find the pH of a solution of a salt of weak acid with a weak base. A question: calculate the pH of a 0.1 molar solution of ammonium cyanide at 298 Kelvin. Take the Kb as 10 raised to power minus 5 and Ka as 10 raised to power minus 9. We have used Ka and Kb as the parameters to decide the strength of acid and base respectively. Higher the value of these constants, more is the strength. For an acid-base conjugate pair, we can have Ka of the acid and Kb of its conjugate. In such case, Ka and Kb are related in a very simple manner. That is, Kw is equal to Ka of the acid multiplied by the Kb of its conjugate. If you look closely, for an acid having the dissociation constant Ka, the dissociation constant Kb of its conjugate is actually the Kh, that is the hydrolysis constant. For a conjugate of a weak acid, Kb is equal to Kw by Ka, that's equal to Kh, or for a conjugate of a weak base, Ka is equal to Kw by Kb, again equal to Kh. The constant for the tendency to react with a strong counterpart, that is, the tendency of a weak acid to react with a strong base, or the tendency of a weak base to react with a strong acid, is actually the reverse or inverse of the hydrolysis constant. Hence, the tendency to react K is equal to 1 by Kh. For a weak acid, it would be K is equal to Ka by Kw, and for a weak base, it would be K equal to Kb by Kw. Now let us discuss about some very simple and obvious terms. These terms also fall in the category of you will do it in the next class and you have done it in the previous class. And even more balanced, you must be knowing it, as if everybody learnt it along with the mother tongue. The terms are as simple and obvious as solute and solvent. For the very first, there is no chemical difference between the solute and the solvent. Looking at a pure substance, it simply cannot be said whether this will be the solvent or the solute. As per the convenience, definitions of solute and solvent have been made, which are simply the conventions. There are as such three definitions of solute and solvent depending on the requirement. The first one, if the components mixing together to form solution are in different phase, that is different state, then the substance which is initially in the same state or phase as the final solution is termed as solvent. For example, copper sulfate solid anhydrous interacts with water to form copper sulfate hydrated. Here, copper sulfate was initially the solid and water the liquid. The final solution that we obtained is a solid. Hence, here copper sulfate is the solvent and water is the solute. If various liquids are mixing up and one of them is water, then irrespective of the amount, water is the solvent. For example, if we have a solution containing 95% ethyl alcohol and 5% of water, then the solution is referred to as 95% alcohol and not 5% water. Simply put, it is concentrated alcohol and not dilute water. Although technically it is more appropriate to call it dilute water. Similarly, we have 98% sulfuric acid and so on. All concentrated solution involving liquids and one of them being water are more appropriately dilute water. But we consider water as a solvent and we take them to be concentrated solutions. For the different components in the same phase mixing up to form solution, the component which is in huge concentration, that is at least 5 times and most often 10 times of any other component in the system is termed as solvent. The concentration of this component remains non-changing throughout the reaction and is considered constant. This definition is the most appropriate for chemical kinetics and equilibrium. If it is not possible to apply any of these definitions to a given system, then it is simply considered a multi-component system or a multi-component solution. We do not try to define solute or solvent. There are certain other terms that are again taken for granted, and they do fall in the same category, that is, you know it, or you will do it in the next class, or you have done it before. These are often confused. The first one, saturated solution. A solution in which no more solute can be dissolved, keeping the temperature and pressure constant, is termed a saturated solution. It has the maximum solute for the given conditions. Then there is concentrated solution. A solution in which the mass of solute is more than the mass of the solvent is considered concentrated solution. It is not a compulsion that we will be able to get the saturated as well as the concentrated solution of a substance. Many a times we get some substances of which we can get either a saturated or a concentrated solution, but not both. Most often, saturated solution is concentrated as well, but in case of sparingly soluble salts like silver chloride, the saturated solution is a very dilute solution. And if we are thinking of ethyl alcohol, we can get a very concentrated solution, but will never achieve saturation as its solubility is infinite. It is completely miscible with water. Till now, we have discussed about the substances which are very soluble. That is, we can get their 0.1 molar solution easily. Now, we consider the substances which do not easily dissolve in water. For example, silver chloride, AgCl. If we add a small pinch, something like 100 milligram of it in 1 liter of water, this also will not dissolve completely. Silver chloride is sparingly soluble salt. We may be tempted to say insoluble. Something like 1.9 milligram of it dissolves in 1 liter of solution. So in this case, we will have to consider an equilibrium at the very beginning itself. That is, at the time we are making the solution, at dissolution itself. So to consider the dissolution of silver chloride. When silver chloride is added to water, a very small amount of it actually dissolves. The rest of the amount is either suspended in the system or simply settles down. It is sparingly soluble. Still, it is a salt and is a strong electrolyte. Whatever amount of it dissolves is completely dissociated. If we add these two equations, we get a solid solution equilibrium. In this equilibrium, on the left hand side is the undissociated solid salt along with water, while on the right hand side there are separated and hydrated ions. In this equation again, one of the reactant on the left hand side is water, which is the solvent and present in a huge excess. Now let us define a term solubility. If we keep on adding a substance to a given amount of solvent, then there would be a possibility that the substance does not dissolve after a certain amount has been added. This amount that dissolves in a unit volume of the solution to give a saturated solution is termed solubility. The units are as per convenience. In most cases, it is given in grams per liter, but in chemistry, and more so in equilibrium, it is in molarity. That is, moles per liter. The symbol which is used, again, generally is S. Solubility, by definition, it is the concentration of the substance dissolved in its saturated solution at a constant temperature, usually 298 Kelvin, and a constant pressure, usually 1 bar. It is given in molarity. Considering the dissolution of silver chloride. When excess of silver chloride is added to 1 liter of water, and mind it, in this case, a small pinch is also excess. A small amount of it is dissolved to give a saturated solution. This small amount dissolved in 1 liter solution is its solubility, generally given by the symbol S. So the equation becomes silver chloride solid plus aqueous in equilibrium with silver ions aqueous plus chloride ions aqueous. Under AgCl is written minus S. AgCl is a solid. Its density itself is its concentration. Dissolving a small amount of it does not change its density or concentration. Further, the concentration of the solid, that is, its density, remains a constant throughout the reaction. Hence, is not included in the equilibrium expression. Here, just to state the fact that S amount of AgCl has been dissolved minus S has been used. The equation tells us that per mole of AgCl dissolved, 1 mole each of Ag plus and Cl minus will be formed. So when S moles of AgCl dissolve, S moles each of Ag plus and Cl minus will be formed. As this equation with forward and backward equilibrium arrows again represents an equilibrium constant is obviously used. This equilibrium constant will be obtained by multiplying the concentration of silver and chloride ions in the saturated solution of silver chloride. There is no denominator in the expression as the left hand side has one solid and other solvent. The concentration of both remains a constant throughout the reaction. The stoichiometric coefficients of both silver and chloride ions are 1 each. Hence, the power of the concentration is only 1. So, the equilibrium constant for the saturated solution of silver chloride is simply the square of its solubility. This is the product of the concentration of ions due to the solubility of salt, hence it is known as solubility product, represented as KSP. Taking another example, and this time of calcium fluoride, in which the stoichiometric coefficient of calcium is 1, while of the fluoride is 2. Calcium fluoride CaF2 also is a sparingly soluble salt. Here again, we consider the moles of salt dissolved in a liter of solution as S. The equation tells us that per mole of calcium fluoride dissolved, 1 mole of calcium ions and 2 moles of fluoride ions are formed. So when S moles of calcium fluoride dissolve, S moles of calcium ion and 2S moles of fluoride will be formed. In this case, the concentration of calcium is raised to the power 1, while the concentration of fluoride is raised to the power 2. The concentration of calcium is S, while the concentration of fluoride is 2S. So, the expression of this equilibrium constant is 4 multiplied by the cube of solubility. Taking the example of aluminium sulfate, Al2SO4 thrice. The stoichiometric coefficient of aluminium is 2, while of sulfate is 3. Again, taking the same convention and considering the solubility as S, we get the equation. The equation tells us that per mole of aluminium sulfate dissolved, 2 moles of aluminium ions and 3 moles of sulfate ions will be formed. So when S moles of aluminium sulfate dissolve, 2S moles of aluminium ion and 3S moles of sulfate will be formed. In this case, the concentration of aluminium is raised to the power 2, while the concentration of sulfate is raised to power 3. The concentration of aluminium is 2S, while the concentration of sulfate is 3S. So the expression for this equilibrium constant is 108 multiplied by the 5th power of solubility. Now let's take a general formula binary salt. Binary salt is a salt which has one type of cation and one type of anion only, simply represented as AxBy. In this general example, the stoichiometric coefficient of A is X, while of B is Y. Again, by convention, we take the solubility as S. The equation tells us that per mole of AxBy dissolved, X moles of A Y plus and Y moles of B X minus will be formed. So when S moles of AxBy dissolve, XS mole of AY plus and YS moles of BX minus will be formed. In this case, the concentration of A is raised to power X, while the concentration of B is raised to power Y. The concentration of A is XS, while B is YS. So the expression of this equilibrium constant is X to the power X multiplied by Y to the power Y multiplied by the solubility of the salt S raised to the power the sum of X and Y. Now we can define the solubility product. The solubility product of a salt is the product of the concentration of the ions with each concentration raised to a power equal to the coefficient of that ion in the balanced equation for the solubility equilibrium in its saturated solution at a constant temperature. Like every equilibrium constant, it is an experimentally determined quantity and depends on temperature. Ionic product. If we mix a solution of NaF with a solution of calcium chloride, the final solution will have two cations and two different anions. Now, 4 different salts can be obtained from it. This solution may or may not be saturated with respect to any of these salts. Here, we are not sure that the reaction is at equilibrium or not. We do not know whether this case the solution is at saturation or not. So what we do is we find the reaction quotient Q, and in this case it is called the ionic product QSP. The ionic product of a salt is the product of the concentration of the ions of a particular salt with each concentration raised to a power equal to the coefficient of that ion in a balanced equation for the solubility equilibrium. For a general binary salt of the type AXBY, QSP is equal to AY plus concentration raised to power X and BX minus concentration raised to power Y. Here, A concentration is obtained from any of the salt in the system, and B concentration again is the total concentration obtained from all sources in the solution. This QSP may be greater, less, or equal to KSP. If QSP is equal to KSP, it means it's a saturated solution. If QSP is less than KSP, it means unsaturated solution and more of the salt can be dissolved. If QSP is greater than KSP, it is forming an oversaturated solution. An oversaturated solution can form a precipitate if conditions are appropriate. Hence, to find if a particular salt will precipitate from a solution containing different ions from different sources, we just have to find the relation of the ionic product with its solubility product.